Okay, welcome everybody. Thank you for coming. A lot of us have been very much looking forward to this event. We have Bill Ross, who is the Richardson Professor of Mathematics at the University of Richmond. Uh, Today, Bill's going to tell us about his eighth book, which we're all excited about, called Operator Theory by Example. It's all yours, Bill.
Thank you. So this is my book launch. Um, I have a good friend, and she's a novelist, and today is her book launch as well. And she's giving interviews with the media and all that exciting stuff. I asked the media not to attend this. I figure we don't need all those distractions anyway. Plus, the media is in New York City right now anyway. So this is my pandemic book. That's what I'm calling it. So in between boxing lessons, online boxing lessons, baking bread, and mastering the art of cocktail making, I worked on this book. With my co-authors Javad Mashreghi and Stephan Garcia. We've been having this book idea in mind for a while, and then when we were all stuck in our homes, we figure, well, might as well actually do it instead of just talking about it. Um, anyway, here's the book. It's the Operator Theory by Example. It's published by Oxford. It's out now. I just checked. Um, uh, one of the reasons that we wrote the book, we didn't just decide, hey, let's just compile a bunch of operators. We kind of had a philosophy of what we're trying to do. We had this opinion that operator theory is sometimes presented in an abstract way. It's presented as an operator on a Hilbert space, and you kind of sort of have to imagine what that is, and you have to imagine maybe what Hilbert space, and uh, maybe you're thinking of a specific example of a particular Hilbert space that you like. So what we decided to do is we wanted to promote the variety of examples of interesting operators, because one of the things we find when you do research is that you have a conjecture about something, and a lot of times it's good to have a bunch of examples that that can prove sort of a testing ground for your conjectures. Um, so here are the main themes of the book. So each chapter is about an operator and not a concept. So we'll talk about that in a moment. So focus on the shift operator, the Volterra, the Cesaro, and things like that, and not necessarily on self-adjoint, normal, subnormal, hypernormal, all these other things. The other thing we do is we include a lot of the original proofs of the theorems. There's a lot of great history around this stuff, and some of those original proofs are some techniques that people don't really do anymore, but they're still just terrifically interesting things. Um, we also have we dove into the history of everything, and we have a lot of historical references in the uh, uh, book, and we go back to the Reese and von Neumann and things like that, to just some of the founders of operator theory. And the other thing we try to do is to keep it simple. We don't find a great need to wildly generalize everything and try to prove the most general or abstract form of anything. We sort of make some comments about the Cesaro operator and kind of stick to that. It would just otherwise it kind of defeats the purpose of presenting examples of operators and not sort of a general abstract discussion of operators. We also don't hold back on any of the details. I remember as a graduate student, and you read functional analysis texts, and you're thinking, how did they get that? And it just, wow, would it have killed them to give another couple of lines to that proof? I would have gotten more out of it. It's also student tested. So between the three of us, Javad has some very good graduate students, and Stephan and I have very good undergraduates. We actually had them read the book. Javad's students work through all the exercises, and with the ones he couldn't do, he would email us, "Hey, how about a hint?" And then Stephan had some great undergraduate students who could work through the book, and whatever she didn't understand, she would send us an email, and we didn't try to explain it away. We would just say, okay, an excellent student didn't understand it, so we need to make it better. So we really focused on the student in engagement with the book. We also, didn't insult the reader with any obviously or clearly or a routine computation shows. I never really liked that in books or papers. So just we didn't do it in our book. And we have over 600 exercises in the book. And we use those exercises not only so students could sort of test some of the theorems, but we also use it to continue the discussion. What happens if you took away this hypothesis? So why is the Volterra operator defined this way and not this way? Why does the adjoint formula work in this way and not the other way? So it continues the discussion. Okay, so what's in the book? So what I'm going to do is I'm going to tell you what's in the book, and then as my novelist friend is doing today, she's going to read selections from her book. So I'm going to kind of do that in a way, but it's not going to be actual reading out of the book. Anyway, so the first chapter is on diagonal operators. So these are exactly what you think they are. They're just put diagonal entries in an infinite matrix, and that defines, well, hopefully it defines an operator on little L2, the square summable sequences. Now you may think, wow, that's a really elementary thing, but diagonal operators are bounded if and only if their eigenvalues are bounded, they're compact when the eigenvalues go to 0. And there's actually a lot of cool things about understanding cyclicity and invariant subspaces of diagonal operators. And there's even ongoing research. If you sort of perturb a diagonal operator a bit, you can try to use it to explore the invariant subspace problems. So next we talk about infinite matrices. So there you have, we all know, if you teach undergraduate matrix theory, these are used to define linear transformations on finite dimensional vector spaces. So now if you have an infinite matrix, you can talk about, does it define a bounded operator on little L2? Now, of course, there's some convergence issues, right? Because you have you use the row by column operation, and every time you do that, you're going to have an infinite series. And well, does that actually converge? And okay, so maybe if you have amazing luck and that actually converges, then you have to talk about whether the output still defines a sequence in little L2. And there's some gems called Schur's theorem, which kind of unpacks all of that. And then there's a great, beautiful infinite matrices. There's Toeplitz matrices, there's Hankel matrices, Cesaro matrices, and all sorts of other things. Okay, I seem to be. Then there's the how about this for an example of an operator, a very specific operator, just multiplication by x on L2 of the interval. That's a nice self-adjoint operator. You can actually completely describe its invariance subspaces. It's a great way to get an introduction to the norm of an operator. How about multiplication by the independent variable on L2 of this circle? This is known as the bilateral shift. Invariance, this is a unitary operator. Its invariance subspaces are described, and they go back to the mid 20th century, and then later on to the 70s, I think. Helson described all the invariance subspaces of this. So again, these are very specific operators, and you can tell everything there is to know about the spectrum, eigenvalues, adjoints. How about the shift on little L2? So I'm sure most of this audience probably knows it as multiplication by Z on the Hardy space. So you take a power series and you multiply it by Z. You can also think about it as the shift on little L2. You take a sequence, you shift it up by one, and you put a 0 in the first slot. This is sort of the model of where operator theory becomes interesting. It's one of the most impactful operators. People are still talking about it. The Cesaro operator, I highlight this one because this is going to be one of the selections I'll talk more about. There's actually a little bit of a resurgence of work done on the Cesaro operator. The Volterra operator, I teach in an undergraduate college, so I call this the antiderivative operator. It's just anti-differentiation on L2 of the intervals 0, 1. This actually has a lot of connections to approximation theory, to inner functions, some terrific stuff. Multiplication operators, these are just multiplication by a bounded function on L2 of measure space. These are extremely important because they model normal operators. They can model unitary and self-adjoint operators. And you can talk about everything there is to know about these, and we catalog them all very carefully. The Dirichlet shift, this is a multiplication by Z on the functions with so-called finite Dirichlet integrals. So these are the analytic functions whose derivative is square integrable with respect to area measure on the disk. So the Dirichlet shift and its close cousins, they model a class of operators called two isometries. And the other thing about the Dirichlet shift is we kind of understand the cyclicity and the invariance subspaces. We almost do. We're like this close. We completely understand multiplication by Z on H2, and the Dirichlet shift is we are so close. we compare this to the Bergman shift, which is multiplication by z on the space of square integrable analytic functions on the open disk. There, the invariant subspaces become impossibly complicated. And I think I'm not going out too much on a limb here, is that we will never understand the invariant subspaces for the Bergman shift. It's just a wildly infinite invariant subspaces. Cyclicity also seems to be a very difficult problem as well, but there's just been so much work done on the Bergman shift, and it's a nice example of a subnormal operator. The Fourier transform. So I teach a lot of physics students. And in fact, I have an undergraduate student writing her senior thesis on the Fourier transform. This is a perfect example of a unitary operator, and it's a very specific thing. The Hilbert transform. This has sort of a complicated formula, but it basically solves the conjugation problem. So if you're given a harmonic function, you want to complete it to an analytic function. So you want to find something called the harmonic conjugate. And if you give me a harmonic function in a certain class, the Hilbert transform helps me discuss the function you need to complete it by to get an analytic function. This has a lot of explorations to what are called Riesz transforms, but these have a very interesting orthonormal basis, and both the Fourier transform and the Hilbert transform have a beautiful set of eigenvectors. It relates to orthogonal polynomials, Bishop operators. We're going to discuss these. These are possibly counterexamples to the invariant subspace problem, or possibly not. We'll go into those more operator matrices. So a lot of times you can create operators from new ones. So if you take, let's say, 4 bounded operators, you put them in a matrix and you make them defined on a Hilbert space, direct sum, some other Hilbert space. There's a lot of beautiful operator theory that we can do with this. And then I call this just constructions with the shift and the backward shift. So S is the forward shift, S star is the backward shift. So you could have S plus S star, S direct sum S star, and S tensor S star. So this is a nice way to introduce people to these important concepts. And then we have a lot of our old friends, a Toeplitz operator, which we start off a discussion of a Toeplitz matrix. So these are matrix which have your constant down the diagonals. These are very classical things explored by Toeplitz. And then there's Hankel operators, which are kind of the same thing, but you're constant on the alternate diagonal. So the Hilbert matrix is a very special example of a Hankel operator. And we actually have a long discussion of the Hilbert matrix. Composition operators. So these are, you take a function in H2, you compose it with an analytic self-map of the disk. Amazingly, that puts you back in H2. It's not obvious that that actually takes place, but it does. And there are a lot of great things about when is it bounded? What is the norm? Are those, when are they isometric? And there's still actually ongoing work. No one understands what the invariance subspaces of a composition operator. I mean, there are some nice results on that, but subnormal operators. So these were originally founded by Bram, and they were popularized by John Conway. He sort of cataloged all this stuff. And then no Bill Ross talk would be complete without a discussion of model spaces and inner functions. And so we talk about compressed shifts. So, and these are used to model certain contractions. So it was a very important work by Naj and Foyas trying to really understand what a contraction operator is. So this sort of plays a small role in a very broad theory. So that's what's in the book. So as you can see, they are all very specific operators and not necessarily classes of operators or operators that satisfy certain properties. So let me give you the operator theory sampler. I've made a selection. I'm calling these interesting operators. And maybe you haven't seen these before. I figured let's not sort of go through ones that everybody knows. And then these are operators that at least I find interesting now. So let's look at the Cesaro operator. So I'm a student of Tom Crete, and he made his name together with David Trutt on proving some very important results about the Cesaro operator. And I've been just getting interested in the Cesaro operator these days, so I'll do that one. So we all teach our Calc 2 students how to add an infinite series as we talk about, the power series and the Taylor expansion of a function. So we talk about what it means for a series of numbers to converge. And if you have a sequence of complex numbers, we talk about the partial sums of that sequence. And if the partial sums converge, then we say a sequence is a summable sequence. But we teach our students that not all you can't add up all infinite series. So a kind of a substitute for it, explored by Ernesto Cesaro, is how about taking the averages of the partial sums? And so a series is going to be Cesaro's summable to L if the averages of the partial sums converge to L. So for example, the Grandi series, 1 minus 1 plus 1 minus 1, and so on, that is a series that does not converge because the partial sums are either 1 or 0. And so that sequence of partial sums doesn't converge. However, if you take the averages of the partial sums, right, about half of them are 1 and the other half are 0. So if you take the average, you get a half. So that is an example. So there's a whole discussion about from Cesaro from how you actually add up a series. And why is this important? To understand Fourier series. So if you take an L1 function, you can actually create a very terrifying examples by Kolmogorov of an L1 function whose Fourier series converges nowhere. However, if you take the Cesaro sum of the Fourier series, it will actually converge almost everywhere. So this kind of inspired looking at the linear transformation of taking an infinite series and now looking at the sequence of averages. And you can do this with a matrix, right? This is a linear transformation. You can always represent it as a matrix. By the way, in the book, where we have this great passion for a matrix representation for these operators because they have very beautiful matrix representations. So here is the way you can represent this linear transformation, and you get this nice patterned matrix. So you get ones, a half, a thirds, a quarter, and so on. And notice when you do the multiplication, you actually get the averages. All right, so connecting this with the Cesaro summability, so if you take the partial sums and you let the Cesaro matrix operate on it, you get the sequence of averages. So that limit is going to give you the Cesaro sum of a series. So a result from 1965 in a paper of Brown, Helmholtz, and Shields shows that the Cesaro matrix actually defines a bounded operator on L2, and the actual norm of the Cesaro matrix is equal to 2. All right, so I feel obligated to give you at least one proof in this talk here. So, and also just because there's some cool mathematics in this, well, one of the things you can show a nice matrix computation. If you look at the identity minus Cesaro operator times its adjoint, you actually get a diagonal operator. That's a cool fact in itself, with a very nice diagonal entries. All right, then you use something called the C-star algebra identity for the norm of an operator. So you take I minus C norm squared, and you get the operator times its adjoint. All right, and you're gonna ask to compute the norm of that diagonal matrix. And it's a known fact that the norm of that is going to be the supremum of the entries, which is 1. All right, so now you do a little adding and subtracting with the identity. You use the triangle inequality for the norm of an operator. And so the norm of the Cesaro operator is at most 2. And then there's you can approximate it from below with unit vectors. It's a technical detail to show that it's actually equal to 2. All right, so these are the kind of things you see in the book. Now, one of the things that people are interested in is deviations from an operator being normal. So you can actually test out that C star C minus C C star is actually not equal to the 0 operator. So it's a non-normal operator. Brown, Helmholtz, and Shields actually give a proof that it satisfies, I don't know, a consolation prize. It's what's called a hyponormal operator. So it's not 0, but at least it's a positive operator. And by the way, Crawford Brawley, he's my mathematical brother. He has a slick way of proving this, which is an exercise in the book, using something called a posinormal operator. The book, we actually give the original proof of this, although it's a little bit complicated. It connects with some gems from when a matrix is a positive definite matrix. That's Sylvester's law. All right, and then the gem in this subject is a result by Crete and Trutt, which shows that the Cesaro operator is unitarily equivalent to multiplication by 1 minus z on some very mysterious but very interesting space. It's the closure of the polynomials in L2 mu. So a normal operator, a subnormal operator is one which has a normal extension. So multiplication by z on H2 mu is not normal, but multiplication by 1 minus z on L2 mu is. So it's a subnormal operator. So it's not at all obvious that the Cesaro operator is subnormal. It's just from the definition, it's hard to see the normal extension, but here you could actually see a normal extension. Just I have this thing these days. If you give me an operator, the first thing I ask, it doesn't have a square root, and can I compute it? So I have this paper with Mark Patak. So a bounded operator is a square root of the Cesaro operator if and only if it's one of these two things. It's kind of a cool factorization. What's interesting about it is notice this matrix here, the rows are the alternating binomial coefficients. So if you take x minus y and write it all out, here are the coefficients, x minus y to the n, here are the coefficients. And then you have these sort of square roots of the reciprocals of the integers. But by the way, in case you're thinking, oh, wait a minute, if I put plus or minus ones down these diagonals, they will formally also define square roots, but they're not bounded operators on L2. All right, bishop operators. So these operators, people don't see them a lot, but I find them very interesting. My advancer is not. So for a parameter between 0 and 1, you can define this operator on L201 to itself. I have to unpack this a bit. So I multiply by x, and then the argument here is I take x, I add alpha, but I do this mod 1. So if I take x, I add alpha, that puts me possibly past 1, but then what I do is I just cut off the integer part. So if I go to 1.2, it's 0.2. You can think of it as like 0, 1 is a circle, and you're just kind of turning things. All right, so the operator was formulated by Everett Bishop, who is known for more of his work on ergodic theory. And the idea was that for irrational alpha, these operators kind of, in a way, turn L2 in such a drastic and dramatic way, it might force it to have no invariant subspaces. That was the idea. So Stephen Parrott, in his thesis, actually worked out the operator theory for these things. And he did it for these, but he worked for a much broader class than this. But he proved that for any alpha, these things have norm 1, and you're not going to get invariant subspaces on the cheap here. You're not going to get them through eigenspaces, right? If you have an eigenvector, you automatically have an invariant subspace. So the point spectrum is the empty set. The other thing he did is for a rational alpha, he described the invariant subspaces. And matter of fact, he did the fine detail of describing both the reducing and the non-reducing invariant subspaces. He also described the spectrum of these things. There's some beautiful geometry that goes on here. So for a rational alpha, the invariant subspaces turn out to be these spokes, right? That's sort of like the spokes of a bicycle. So in the book, we actually worked it out for alpha is equal to a half. So how much more specific can you get with that? All right. When alpha is rational, he described all the invariant subspaces. Um, Now you're thinking, what about the irrational case? So Davy said, well, for almost every alpha, the bishop operator actually has non-trivial invariant subspace. As a matter of fact, it has non-trivial hyper-invariant subspaces. Um, the proof of this theorem involves a lot of number theory, like how close can you can approximate every in basic analysis you teach your undergraduate, you can approximate every uh, irrational number with rational numbers. Now you want to approximate with only certain types of rational numbers. So various number theory going on here, and he uses that to show, Davy does, it has non-trivial invariant subspaces. So there are some highly irrational alpha, and no need to get into what that means, where we actually don't know yet, or at least I hope no one's going to tell me afterwards, that we don't know whether it has non-trivial invariance subspaces or not. So I think these are just an interesting class of operators. They're not normal or self-adjoint or unitary or any other special property. So, and they connect to the invariant subspace problem. All right. So here are some just interesting specific operators. So kind of every operation you can put between the shift and its adjoint. The advancer here doesn't seem to like me today. So the shift is the operator on little L2. It just moves everything up by 1 and puts a 0 in the first slot. You can compute the unilateral shift as an isometry, so it has norm 1. You can compute the spectrum, the point spectrum, its adjoint. Well, it gets a little interesting here because the adjoint actually has a kernel now. So you take a sequence, you shift it back once, and you lose a 0. There's a nice matrix representation for the shift. I make my matrix theory students actually write out the matrix of every linear transformation we ever encounter. So maybe that's just me, but all right. Now, what could you say just about S plus S star? Well, that is a self-adjoint operator. And then there's this general theory of the spectral theorem, beautiful theorem to look at, but it's very difficult to understand it in a tangible way for a specific operator. So you're always very excited when someone can actually tell you what the spectral theory is. And Hilbert did in 1912. So let me normalize things so it looks like what Hilbert did. So if I take S plus S star, for those of you who like Toeplitz matrices, this is the Toeplitz matrix with halves on the upper diagonal and 1/2 on the lower diagonal surrounding the main diagonal, or it's the Toeplitz operator with cosine theta as this symbol. The spectrum is -1 to 1. It's a cyclic. The point spectrum is empty. It's a cyclic operator. So it's multiplication by x. And it's not only on some general L2 mu space. Hilbert actually tells you what the weight is. So it's L2 of a weight on Lebesgue measure on -1 to 1. And by the way, Putnam did this for S 1/2 S to the n plus S to the S star to the n. So we know this is cosine and the Toeplitz operator with cosine and theta. Well, how about S plus S star? So these are a way to introduce operators on the direct sum of two Hilbert spaces via a very tangible way and not so abstractly. So S plus S star, well, a vector in the direct sum of two Hilbert spaces is just going to be a direct sum B. So you can think of it as a pair. And what does it do? Well, it operates by S on the first slot and then S star on the second slot. And this has sort of a matrix representation, right? You take a pair and you operate it on it with a matrix. And so you understand it that way. And this is a kind of a gentle way in understanding matrices of operators. You can work out everything you want to know about just norm spectrum, point spectrum, its adjoint. This formula makes sense because of this formula, right? If you take the adjoint, right, you just put stars along the main diagonal, and that is actually what takes place. All right, S plus S star is a non-self-adjoint operator, but there's a consolation prize here. If you look at conjugation, right? So this is an anti-linear isometry, right? It's just if you just take a sequence in little L2 and you just put conjugates on every entry, and you define this. It's called a conjugation. Well, even though S plus S star is in self-adjoint, if you put the C's on either side, you actually get the adjoint. And this is a special example of a broad class of operators called a complex symmetric operators. And I worked out with Christina Kamara on some of the invariant subspaces of S plus S star in a very recent paper. Dan Timotine described all of them. So S plus S star, you may think, well, what's to be known? Well, there's a lot to be known, and it's a very interesting operator. How about S times S star? S, the tensor product with S and S star, right? So rather than get into the whole discussion of tensors of Hilbert spaces, here's a version of it, right? Kind of the Hadamard version of the Hadamard multiplication of S and S star, where, you just, for every entry of S, you just put S star, right? So you have ones below the main diagonal and you just put S star there. All right, so this is very interesting because it acts on infinite number of copies of L2, right? So you put an element in L2 in each one of the entries going along the main diagonal, and then you let this operator act on it. All right, so a lot of times, I think that what we're trying to promote in this book is understanding just as many specific examples of operators. This is a particularly complicated one. Now, the original operator theory maybe doesn't seem to be very complicated. All right, it has a readily identifiable norm, the spectrum. You can compute it without too much effort. You can compute its adjoint. I'm going against the idea I'm trying to promote in the book. I'm not supposed to use readily identifiable, the words obvious, easy, things like that. So take back everything I just said. You work your butt off to compute these things. All right, so here's a cool thing. S tensor S star is actually unitarily equivalent to this rather interesting operator on H2 of the bidisk. So if you take H2 of the disk, these are square summable power series of and if you have a power series and two variables, H2 of the bidisk is the same thing, right? So this is kind of interesting. You take a function of two variables and then you sort of in one variable, you take the backward shift. This kind of looks like the backward shift. And in the other variable, you take the shift. So it's unitarily equivalent to that. Well, I find that itself is an interesting thing, and you're bringing in H2 of the bidisk. Another thing you can do is you could actually show that S tensor S star is unitarily equivalent to the direct sum of Jordan blocks. So let me just put that for you here. So if I take the 0, 0 Jordan block, the 1 by 1 Jordan block, the 2 by 2, 3 by 3 with the ones, S tensor S star is unitarily equivalent to that. Now, I'm not saying it makes your life any easier. That's a very complicated operator, but at least you're associating it with two kind of interesting things. H2 of the bidisk with this weird backward and then forward shift type of thing. And with this description, this Jordan block description, we can describe the reducing subspaces, so the ones that are invariant for both this operator and its adjoint. It's a little too complicated to do in a short talk like this. But the invariant subspaces are very rich, and I don't know what they are. So anyway, the book is out. I wish I was with everybody so I could sign copies, and everybody would buy me drinks, and we could talk to the media and all that other cool stuff. So anyway, thank you so much for coming, and this is a great invitation. So
Thank you for a
there we
really
go.
wonderful talk, Bill. Let's give Bill a hand. Okay, do we have any questions? Oh, I notice also Javad is here. Another author of the book. Hi, Javad. Any questions?
So Javad, I hope I said the correct things in the book, but we'll see.
Okay, if nobody has maybe formal questions, I'm going to stop the recording now, and then we can chat more.